Good day, class. Welcome to another MetE14 video lecture. For today, we will be discussing Central Composite Design or CCD. So let's just recall our last lesson. So we did RSM and specifically the method of Steepest Ascent. So first we did step one, which was to choose a region for initial investigation. Then we fitted a first order mathematical model. Then we investigated the model and checked for lack of fit, and if the model adequately fitted the data, then we can perform the method of steepest ascent. Then after method of steepest ascent, we observe the response, and if there is or a discrepancy in the observed response, or kumbaga, the model failed to fit or the model broke down, then we iterated back to step one and did the process again. So in our last lecture, we stopped here in step two, in step three, when we checked for the lack of fit. If the data does not adequately, or if the model does not adequately fit the data, then we need to perform a central composite design. So if you remember our lesson, we showed that there is indeed a lack of it now, because if you look at here, the computed critical value is, or the computed F value is greater than the critical F value, which indicates that the LOF, or lack of fit, is indeed significant. And if it's significant, then meaning the model does not fully fit the data we have. So now we need to upgrade it to a central composite design. And for central composite design, this is usually done so that, or this is done so that we can create a second order or a quadratic model. So take note, when we were doing the method of steepest ascent, we were only dealing with linear models now. So this time, gagawa tayo ng second order quadratic model. Okay? So for the CCD, bukod dun sa factorial points and the center point runs. So again, factorial points here is yung original 2 to the k settings, yung mga low and high settings, that's the -1 and the +1 coded settings. Then this center point runs were the 0 coded settings. And now we add what we call as star points. So star points is defined by an alpha value. So the alpha value here, take note, is different from the alpha for level of significance. So usually we have alpha is equal to 0.05. But this alpha value for star points is widely different now. So I'll show it later on. So to perform CCD using star points, we follow these 4 steps now. So first we code the levels as -1, +1, and 0. So we already did this now when we did the initial investigation and the RSM. Excuse me. Now we calculate, the next step is to calculate alpha according to the number of factors. Then after calculating the alpha, we list down the coded star point settings. Then we convert those coded star point settings into a actual or a natural setting. So we start with calculating alpha. So alpha is just the distance of the star point from the center point in coded units. So here we have a table that is a guide in choosing our alpha value versus yung number of factors na meron tayo. So if it's 2, we have 1.4142. We have 5 factors, it's 2.3784. So these alpha values can be computed using this formula now. 2 to the k over 4, where k here is our number of factors. So we have for the example we did was we were trying to excuse me, we were trying to investigate how yield was affected by temperature and time. So time and temperature, so that's two factors. So we have 2 raised to 2 over 4. So that's 2 raised to 1 half, or just the square root of 2, and square root of 2 is equal to 1.4142. Okay, so if you look again, for example we have 4 factors, so that's 2 raised to 4 over 4 is 2 raised to 1, and 2 raised to 1 is equal to 2. Okay, so you can use this equation so that you can solve for the alpha factor or the alpha value. Excuse me. So here, this is an illustration of how the coded or the how the design of experiment would look like now. So if you look at the square, the corners of the square represent your factorial points now, or this is the usual 2 to the k combinations. So if you look here, we have this is plus 1, meaning both factors are set to high setting, while this point is minus 1, where both factors is set to low settings. Okay, and here we have x1 is plus 1 or high setting, while x2 is at low setting, and this is vice versa. Okay, so apart from this, when we did MSA, so this is just usual 2 to the k factorial design. Then when we did RSM and MSA, we added the center point runs. So center point runs were coded as 0, so that's the center value here. So that's we have x1 is 0 and x2 is also 0, so it's located at the origin. Now we add several other points now. So the number of star point settings will just, the additional star point settings we will add is just equal to 2 times k, or 2 times the number of factors. So if we have 2 factors, so that's 2 times 2 is equal to 4. So we add 4 additional star point settings. So here, the star point settings is a combination of 0 and a plus or minus alpha. Right? So we have, for example, this star point setting here is when x1 is plus alpha, while x2 is 0. Here we have x1 is 0 and your x2 is plus alpha. Okay? So, and we can do it again for these 2 other points now. Okay, so when we do that, we can now complete the coded settings. So this is a table of your coded settings. So this is just all the combinations of zeros and plus or minus alpha. Okay, so we have 0, 1.414, 0, minus 1.414, 1.414, 0, and minus 1.414, 0. So take note, this the arrangement here is arbitrary now, but this is just all the possible combinations. Okay. So now that we have our coded settings, coded star settings or star points, now we need to convert this into actual or natural settings. So to convert it, we use again the formula now. So that's x here is our coded setting, x prime is our natural setting, CP is the center point setting, while HS here is the high point setting. Okay, so if we rearrange this formula, we should be able to get x prime is equal to x multiplied by HS minus CP plus CP. Okay, so let's just look back at the data we have now. So let me navigate back. So if you remember, we were doing MSA and we actually ended with at the 11th run now. So if you look at the 11th run, the yield actually dropped from 80.3 to 79.2, meaning the model did not, or the model broke down in a sense now. So when the model breaks down, we go back to breaks down, we need to iterate back to step 1, wherein we need to investigate a new region. So here since it's 85 and 90, we can choose a time of 80 and 90 minutes to encompass these data points. No? And for temperature, we can use 170 and 180 degrees Fahrenheit. Okay, so that is now our new region for investigation where we try to create a new model. So let me pull out the Excel panel. So when we did this, so we have now our 80 is our low setting for time, 90 is our high setting. Low setting for temperature is 170 and high setting is 180. Then we had our center point runs. So this is my factorial runs, this is my center point runs. Okay. Now, when we did the lack of fit in class, we noticed that there indeed was a lack of fit in the model, and so we proceeded with CCD, which is the discussion point in this video. So, we are now ready to calculate our star point settings, your natural settings. So let's just fill this up. So we add 4 more rows here, which will be our additional star point settings. So we have 1.414, this is our alpha value. 1.414, we have 1.414 and negative 1.414. And this will be 0, 0, 0, and 0. So again, this is just our coded star point settings. So we have to compute the natural settings using the formula I showed earlier in the previous part 1 video. So we have this is equal to your x value or the coded value multiplied by your high point setting. So for time, the high point setting is 90 minus the center point setting, which is 85, plus your center point setting. Should give you 92.7, and I can drag it down. Now here it's coded value. Now this is for x2 now, the second factor temperature, multiplied by high point setting is 180 minus your center point is 175 plus center point is 175. So I can drag this down again. So I should get something that looks like this. So after getting your star point settings, you need now to do the experiment itself. So suppose that we actually did the experiment now. So I'll just pull out the slides. Wait a minute, class. Alright, so for example, we did the experiment. Now we already did the factorial experiment, so no need to do this. We already also did the center point setting, so we only need to do 4 additional settings, which are this coded or this star point settings here. So suppose that these are our new values. So I'll just copy this. So this is what we got from our experiment. The Excel file. And make sure it's correct. So it's 1.414, negative 1.44, 1.44, negative 1.00. So it's the same. Okay. So now we have completed our data table for CCD analysis. Now we need to compute the second order model. To compute the second order model, we should get an equation that looks like this. So this is the second order model, and if you look at it, the equation is of the second order, and you can see the pattern. So it's b0 plus b1 x1 plus b2 x2 plus b11 x1 squared plus b22 x2 squared plus b12 x1 x2. So let's say for example we added a third factor, then we should have b3 x3, and we should have also b33 x3 squared, and for the interactions we have b13 x1 x3 and b23 x2 x3. So but I think for this course we will only limit ourselves to two factors, no? Pero depende din kay Sir Roderick, baka biglang mag three factors, no? So just try to look at the pattern, okay? So pero for this video lecture I'll be showing you two factors only. Okay, so to solve this different constants, all the b constants, the b0, b1s and b2s, we use this formula. Okay, so let me just copy each of this formula. Okay, I'll copy it to my Excel file. Okay. Now let's rearrange it. So, where's my B1 to that? Okay, so let's start off with the simple ones. I'll just write B0, B1, B2, B11, B22, B12. Okay, so the first one is B1. So let's start off with these top three equations now. So B1 is just the summation of the product of x1 and y. So we can compute it by typing sum product ng x1 for take note class that all of these x's here are the coded values, not the natural settings. Okay, so sum product of x1y, and for b2 it's the sum product of x2 and y. Okay, divided by 8, I'm sorry. So there should be a divided by 8 in the formula. So that's divided by 8. Also this one is divided by 8. Okay? Just insert. I'll move this para di magulo, no? So last one, for the simple equations is your B12. B12 is just equal to x1, x2, and y. So that's sum product x1. So we can choose the coded values x2 and y. Okay, and that's divided by 4. Okay, so we have that looks about right now. Okay, so next we compute these three equations. So this is actually a set of equations. This is three equations, three unknowns, and just like our multiple linear regression analysis, we converted this into matrix form so that we can solve it easier now. So it should be in the form A times B is equal to Y. Okay, so first let's fill in the A matrix. So the A matrix is just the coefficients of all of these equations on the left side. So that's N, then we have 10, then we have 8, 8, 8, 12, 4, 8, 4, and 12. So take note again that the A matrix is symmetrical around the diagonal. So 8 is equal to 8, 8 is also equal to 8, and 4 is equal to 4. that we've completed our A matrix, and actually we can solve for n already now. So we have 4 factorial settings, 5 center point settings, and 4 star point settings. So that gives us a total of 13. And we can check by selecting this and looking at the count, it's 13. So this is our matrix A. Let me just transfer this here now. It's matrix A, and we are multiplying it by matrix B, and matrix B is just the variables themselves. So it's that's B0, B11, B22, and is equal to your Y matrix. Your Y matrix here is, let me just highlight this no, para hindi nakakalito. Y matrix is equal to the right side of our equation. So we have the first value is just the summation of the Y for the yield. Then for this next two, we actually have the square of the coded values. So let's type in the new column. So let's call this x1 squared, x2 squared is just equal to square of this value. Drag this down. Take note, this is 1.999, which is very close to 2, and it should be equal to 2 because if you remember, this is just square root of 2. Okay, so if you want, we can just type this in as 2 now. Then we can copy this one. This square of the coded settings for x2. So again, we can convert that to 2. Now we can do the second element now. So that's the sum product of x1 squared, which is this array, multiplied by your y array, which is this one. Similarly, we have sum product for the x2 squared. So that's x2 squared is this one, multiplied again by y. Okay. So now we have our A, our B, and our Y matrices now. So if you remember from multiple linear regression analysis, and if you're taking ES21 or any linear algebra class, then you should know that if A times B is equal to Y, then the inverse of A, I'll say A prime, multiplied by Y should be equal to B. Okay, so let's first take the inverse of A. Now to do the inverse of A, we highlight a 3 by 3 cell where we want to input our inverse. Press equals M inverse, that's matrix inverse. Then pick our matrix function A. Now to do array formulas in Excel, instead of doing a regular enter, we need to hold down shift and control now. So if we hold down shift and control like so and press enter, we should be able to fill out the 3 by 3 matrix. So if you do not enter, or if you do not press down shift and control, nangyari is you only fill out the first element now. Okay, so this is A inverse, and we are now computing for B, which is just equal to A inverse multiplied by your Y. So to do that, let's first select our our 1 by 3 matrix here, and type M mod. First array is A inverse multiplied by your Y array. Okay, again, press Control and Shift, then press enter. So you should get this value. Now, this is our B0, this will become our B11, and this is our B22. Okay, so now we can complete this one. This is equals B0 This is B11. This is B22. Okay? So, para hindi masyado manggulo, let me pasensya na medyo maingay sa labas, no? So, hanggang 2 decimal para medyo malinis tingnan, no? So, let me remove all of these equations, no? Para hindi masyado magulo. And let's look again at the second order form, no? And let me copy this. So our second order equation should look like this one. Let me bring down. It should look something like this. So y is equal to b naught. B naught is 79.5. Our b1 is 0.04. Our B2 is, this is negative, let's change this to minus, negative 0.16. B11 is equal to, again, negative, so that's 0.57, and let's convert this to a minus sign. B22 is negative, once more, minus 0.19. This is a minus sign, minus. This is and last is B12, which is 1.15. Okay, so this is our final second order model, and now we can proceed to optimizing this model. So if this were a linear model, if you follow the steps, it should be, if it was a linear model, then you do MSA or method of series effect. But for second order equations, you cannot do let me just check if we got the same answers now. Alright, so it's the same answer. Okay, so again, if you are doing CCD, you produce a second order equation, and for second order equations or higher order models, you can MSA is not applicable anymore. So we need to plot the 3D optimum point. And to get that, we actually just have to do the partial derivative. So if you remember math, I think this is discussed in math 53 now, or 54, I think. To optimize a particular equation, you just need to get the partial derivative. Okay, so for example, if I want to optimize x1, then I just get dy, the partial derivative of dy over dx1. Then if it's x2, get the partial derivative of dy over dx2, and so on and so forth. So if you can't remember how to do partial derivatives, then maybe you should review your notes now on how to do them. So that's how you do your optimization for 3D for higher order models. And if you have a powerful software, you can actually plot the surface of the model of the higher order model. It should look something like this. And if some softwares from the 3D model, you can also plot the contour. Alright, so that ends our lecture for CCD, and I wish you good luck in the exam this Monday. Again, it's 9 to 12, and we'll be having late exams for those with morning classes. Siguro, if you want, we could have a review session, sort of consultation sa Friday siguro. I'm free whole day on Friday, so maybe you can email me if you want a class consultation. Okay, so good luck guys, and have fun studying. Kalimutan like, subscribe. class, I've noticed a small minor correction, although it doesn't affect our data. This should be 180, no? Because it's high, low, high, low, low, low. This is high, low. This should be high, high, right? So this should be 180. And if you notice, walang nagbago, no? Since all of our equations involve only the coded settings. So, hindi naman apektado ng natural settings yung ano natin. So anyway, I'll be sending, maybe I'll send this file, yung data sheet, pati itong answer sheet, no, para makapag-practice kayo and tingnan nyo siya in more detail. No? And I suggest na when you're trying to study, no, try to actually do the formulas and stuff para mas masanay kayo na kung paano gamitin yung different formulas natin. Kasi mahirap pagka nakatingin lang kayo sa kung ano yung step-by-step process tapos hindi nyo siya pinractice, no? Or ginawa mismo. Okay, so maybe once I've sent this data sheet, no, pwede nyo din siyang i-analyze na din yung lack of fit niya. Kasi di ba sa class pinakita ko lang na yung final ANOVA table tapos naka-indicate doon na meron ng lack of fit. Pero pwede din siguro na kayo mismo mag-solve na para tingnan nyo kung tama nga na merong lack of fit. And para ma-check nyo yung kung tama yung ginawa nyo, I'll also send the answer sheet as well para ma-check nyo din kung saan kayo nagkamali or ma-double check nyo yung answers nyo. Okay? So, again, have fun studying, guys. Hope you do well sa exam. And I think, sana mas mataas yung scores nyo. Ngayon. Okay? Good luck. Have fun. Like and subscribe.